Hello, in this video we are going to talk about Bayes' theorem. And Bayes' theorem is a fundamentally important theorem in probability which takes our conditional probability that we looked at in the last video and allows us to flip the condition. A bit of background: Thomas Bayes was a Presbyterian minister in the 1700s and he never published his work. But we know he came up with this and proved this, and this theorem then was later named after him. And more than just this theorem was named after him, a whole philosophy around how we think about probability is named after him, Bayesianism. And Bayesianists believe that there's no sort of fundamental probability of an event occurring. All probability is updating what we know. What do we know? What conditions are there? And can we work out the probability based on that condition? The other school of thought in probability is called frequentism. And they don't believe that. They believe things have a specific probability. It doesn't matter in the end which one you believe in. I haven't made up my mind. I haven't really thought about it. And the reason is both schools of thought use all the same tools as each other to work things out. They just think deeper about it in a different way. But they use all the same tools, all the results hold, it doesn't matter. So here is Bayes' theorem, and you can actually derive this yourself, and I will encourage you to do that based on our formulas for conditional probabilities that we had before. If you take your formulas for the two conditional probabilities you see in here, you should be able to see that you can manipulate them to make this and just rearrange the equations. And this is a tool that allows us to flip the probability. So if we know the probability of A given B, and we know the probability of B and the probability of A, then we can work out the probability of B given A. Okay, so it reads here, the probability of A given B multiplied by the probability of B is equal to the probability of B given A multiplied by the probability of A. Well, written in this form, all we are saying is the probability of the intersection of A and B is equal to the probability of the intersection of A and B. But written in this form, it becomes incredibly useful. Let's look at an example. So dangerous fires are rare. But seeing smoke is fairly common because of barbecues and this, that and the other. On a given day, the probability that there is a dangerous fire is 0.01. Well, the probability of seeing smoke is 0.1. We also know that 90% of dangerous fires make smoke that we can see. So knowing all this information, we want to know, if we see smoke, what is the probability of there being a dangerous fire? Okay, think about the events we have here. We have two events, the event F, that there is a dangerous fire, and the event S, that we see smoke. From the question, we had the following information. We had that the probability that there is a dangerous fire is 0.01. We had the probability of seeing smoke is 0.1. And we also know that 90% of dangerous fires make smoke. So the probability of having smoke, given that there's a fire, is 0.9. Now we want to know, what is the probability that there is a fire if we see smoke? What is the probability that there is a fire if we've seen smoke? So we want to flip that condition. So using Bayes' theorem, that is the probability of smoke given fire multiplied by the probability that there is fire divided by the probability that there is smoke. That is 0.9 multiplied by 0.01 over 0.1, which is equal to 0.0 So that probability that we got out was surprisingly small, I think, considering 90% of all dangerous fires give off smoke, that if we see smoke, whether there's a fire or not, I thought was surprisingly small. Here's another example, and I've deliberately chosen the number so that this is a little extreme. But here's another example. The disease dragonpox is very rare. The probability that a wizard will get dragonpox is 0.00001. It's very rare. There is a test for the disease, and this test is known to be 99.5% accurate, which I think is quite high. If Hagrid tests positive for the disease, what is the probability that he actually has the disease? Let's start working that out. Okay, again here we have two events. D, the event that Hagrid has dragonpox, and T, the event he tests positive. What do we know from the question? We know that the probability of having dragonpox is rare. It's 0.00001. So that must mean that the probability of not having dragonpox is 0.99999. A test for the disease is 99.5% accurate. Accuracy means that it tests positive when you have dragonpox and tests negative when you don't have it. So the probability of testing positive given that you have dragonpox is 99.5%. And the probability that you test negative, so you don't test positive, given that you don't have dragonpox, is 0.995. Now that also means that, so all of these also means that how you not having dragonpox is 0.99999. The probability that you test negative given that you have dragonpox is 0.005, and the probability that you test positive given that you don't have dragonpox is 0.005. Now it should also be said that in real life, in real medical tests, these two things are not necessarily the same. These are called the true positive and true negative rates of a test. These are not necessarily the same in real life. But in our example, we are saying that the accuracy corresponds to both of these things. We know that Hagrid has tested positive, and we want to know the probability that he has the disease. So we want to know, I'll write it down here, the probability that he has the disease given that he's tested positive. So using Bayes' theorem, we can write that as the probability of testing positive given that he has the disease times the probability that he has the disease over the probability that he tests positive. We know two of those things. We don't know the bottom. We don't know the probability of just testing positive. So let's have a think about that. What do we know about testing positive? We know the probability of testing positive if you have the disease is 0.995, and the probability of testing positive, apologies, I forgot to put a bar on that, but the probability of testing positive if you don't have the disease is 0.005. So this will happen with probability that you have dragonpox, and this will happen with probability that you don't have dragonpox. And that's the only things that could happen. You can test positive, you can either have dragonpox or not. Nothing else can happen. So we're using something now called total probability, and it follows quite logically that the probability of having the disease is going to be the probability that you have the disease given that you've got dragonpox multiplied by the probability of you having dragonpox plus The other thing that can happen, which is the probability of you testing positive for the disease, given that you don't have dragonpox, multiplied by the probability that you don't have dragonpox. In this case, this is 0.995 times 0.00001 add 0.005 times 0.99999, which gives us something roughly 0.0051. So now we can fill in our Bayes' theorem equation. So what is the probability of testing positive given you've got the disease? 0.995 multiplied by the probability you have the disease, divided by this probability that you test positive in general. That gives us 0.0019. And that seems really strange. That seems like, well, I've tested positive and the test is really, really accurate, 99.5% accurate. So I've tested positive for the disease. Surely I should know more than the probability that I have the disease should be more than 0.0019 now. Surely I should know much more accurately than that. So what's going on here? Well, the probability you have the disease is so small that this rate, the false positives, the probability you have the disease and you don't have it, even though it's small proportion-wise, because the number of people who don't have the disease is so big, the number of people who have false positives is really big compared to the number of people who have true positives. And so this is very, very small. And you might think, well, what's the point of this? What's the point in having this test if it's gives us such little information? It's really, really accurate. It just gives us such little information. Well, what did we know before having the test? This was how much information we knew about having the disease or not. After having the test, this is how much information we've got. This is actually 195 times more than this. So we have gained a lot of information here. So I think that really shows the power of thinking about things in terms of conditions and being able to manipulate conditions. In this example, this dragonpox example, it showed that even though the test was really, really accurate, we weren't gaining that much information from it. Why? Because the disease itself was so rare. But again, I chose numbers specifically here to show an extreme example. That doesn't mean you should go around not testing for things just because it doesn't give you much information. No, and healthcare professionals obviously know what they're doing with this and they understand all these conditions, they know what they're doing with this. I just thought this was a really interesting example to prove the power of conditions.